6 miles beneath Yellowstone, scientists just drilled into something that shouldn't exist. The drill bit hit temperatures that would vaporize steel. The rock down there is so hot it's basically liquid. And what they found changes everything we thought we knew about supervolcanoes. This isn't a disaster movie. This is happening right now. And the implications? Absolutely wild. Keep watching. Because what they discovered could either save us or doom us all. Let's start with what Yellowstone actually is. Because most people get this completely wrong. You've probably heard it called a supervolcano. That's accurate. But calling Yellowstone a volcano is like calling the Pacific Ocean a puddle. Technically true, but missing the scale entirely. There's no cone, no peak, no dramatic summit covered in snow. Instead, there's a massive crater spanning 34 miles by 45 miles. That's 1,500 square miles of collapsed volcanic caldera. You could fit the entire city of Los Angeles inside it. Twice. Underneath this peaceful-looking landscape of geysers and bison sits a magma chamber so enormous it defies comprehension. The shallow reservoir alone is 37 miles long and 18 miles wide. It contains enough molten rock to fill the Grand Canyon 11 times over. And that's just the shallow one. Below that, there's an even larger chamber. We're talking about 11,200 cubic miles of partially molten rock. That's more magma than every volcano on Earth has erupted in the past 10,000 years. Combined, all sitting there under Wyoming, just waiting. The last time Yellowstone properly erupted was 640,000 years ago. That eruption released 240 cubic miles of material into the atmosphere. Mount St. Helens in 1980? That was 0.25 cubic miles. Yellowstone's last major eruption was nearly 1,000 times larger. The ash blanketed half of North America. The climate cooled globally for years. And this has happened at least 3 times that we know of. Roughly every 600,000 to 800,000 years, Yellowstone wakes up angry. Now before you start panicking and Googling real estate in New Zealand, here's the thing. Scientists are actually trying to prevent a catastrophic eruption, not trigger one. Which brings us to the drilling project that sounds absolutely insane until you understand the logic behind it. The U.S. Geological Survey, in partnership with NASA, launched the Yellowstone Volcano Observatory Drilling Project in 2016. Their goal? Drill directly into the supervolcano's heat source and tap into the geothermal energy system. Sounds simple, right? Just drill a hole. Except this isn't drilling into normal rock. This is drilling into one of the most geologically active and dangerous places on the planet. The deepest hole ever drilled is the Kola Super Deep Borehole in Russia. They reached 7.5 miles down, before the drill bit basically melted. The rock was so hot, so pressurized, that it behaved more like plastic than stone. Yellowstone's drilling project aims for 6 miles deep. Temperatures exceed 800 degrees Fahrenheit. That's hot enough to melt lead. Hot enough to make diamonds. The equipment has to be specially designed to not disintegrate. They're using diamond-tipped drill bits, cooling systems that pump ice-cold water down constantly, and sensors that can somehow survive in what's essentially a subterranean oven. The whole operation costs hundreds of millions of dollars, and it's worth every penny. Here's why they're doing it. Yellowstone's magma chamber is heating up. Not catastrophically, not imminently, but measurably. Ground temperatures have risen. The caldera floor has lifted in some places by more than 2.8 inches per year. That might not sound like much, but for a geological feature, it's sprinting. Geysers that have been dormant for decades suddenly started erupting again. Steamboat Geyser, the world's tallest active geyser, was quiet for 50 years. Then in 2018, it started erupting regularly. Something down there changed. Scientists realized that if they could drill into the heat source and release some of that thermal pressure, they might prevent a full-scale eruption. Think of it like releasing steam from a pressure cooker before it explodes. Except this pressure cooker is the size of Rhode Island and contains enough energy to end civilization as we know it. No pressure. The drilling began in earnest in 2018, away from the most active thermal features. 1 mile, 2 miles, 3 miles. Everything was going according to plan. The rock samples they brought up were exactly what they expected. Ancient volcanic deposits. Layers of compressed ash from previous eruptions. Granite that had been metamorphosed by incredible heat and pressure. Standard stuff for Yellowstone. Then they hit 4.2 miles down, and everything changed. The drill bit encountered a layer of rock that shouldn't exist at that depth. Quartz crystals. Enormous ones. Some samples contained crystals larger than a human hand. But here's the weird part. These crystals had formed recently. Geologically speaking, recently, within the last 10,000 years. Maybe even more recently than that. Quartz crystals of this size take hundreds of thousands of years to form under normal conditions. They need stable temperatures, stable pressure, and lots of time. But these formed fast, really fast. The only way that's possible is if the conditions down there are far more extreme than anyone predicted. The temperatures must be higher. The chemical composition of the magma must be different. Something is happening beneath Yellowstone that our models completely missed. The team kept drilling. At 4.7 miles, they hit something else. Water. But not normal water. Supercritical water. At extreme temperatures and pressures, water enters what's called a supercritical state. It's not quite liquid, not quite steam. It has properties of both. Dangerously reactive. Supercritical water can dissolve minerals that normal water can't touch. It can transport massive amounts of heat. And most importantly for our story, it can accelerate chemical reactions by factors of thousands. The presence of supercritical water this deep means Yellowstone's geothermal system is far more active than anyone thought. The heat isn't just sitting there in a magma chamber. It's moving, circulating, being transported upward by this superheated water in ways we didn't understand. This discovery changed the entire model of how supervolcanoes work. And it raised a terrifying question. If this system is more active than we thought, does that mean an eruption is more likely? They found something that made scientists reconsider everything. Minerals that only form in the presence of liquid magma. But not ancient magma from hundreds of thousands of years ago. Fresh magma. Active magma. Right there. Right then. The drill was getting close to liquid rock. Molten material that was actively part of the magma chamber. They had reached the boundary. This was simultaneously exciting and terrifying. On one hand, they had proven they could reach the heat source. The plan was working. On the other hand, they were drilling into active magma. If something went wrong, if the borehole collapsed, if pressure released unexpectedly, they could trigger the exact disaster they were trying to prevent. It's like defusing a bomb while also trying to understand how it works. Except this bomb is the size of Wyoming. The decision was made to continue. Carefully, very carefully. Q. Bacteria. Living bacteria. 6 miles beneath the surface, in temperatures exceeding 700 degrees Fahrenheit, in water so chemically hostile it should sterilize everything. There was life. Not fossil bacteria. Living, active, reproducing microorganisms. These weren't any bacteria we'd seen before. They were extremophiles. Organisms adapted to survive in conditions that would kill anything else on Earth. But these were beyond even the hardiest extremophiles we discovered in deep ocean vents or Antarctic ice. These bacteria were essentially eating rock and breathing sulfur. They were surviving on pure geothermal energy in an environment more hostile than the surface of Venus. And they were thriving. This discovery has implications far beyond Yellowstone. If life can exist in these conditions on Earth, it can exist in similar conditions on other planets. The subsurface of Mars. The ice-covered oceans of Europa. The methane lakes of Titan. Anywhere there's heat, minerals, and water, even in the most extreme forms, life might find a way. NASA immediately got more interested in the project. This wasn't just about preventing a volcanic catastrophe anymore. This was about understanding the fundamental limits of life in the universe. But back to the drilling. At 5.9 miles, just 600 feet from their target depth, something unexpected happened. The drill hit a pocket, a void, a cavity in the rock roughly the size of a school bus. It was filled with superheated steam at pressures that would crush a submarine. The temperature inside this pocket was measured at 842 degrees Fahrenheit. The drill broke through, and for a moment there was concern that the borehole would collapse. But the engineering held, barely. When they analyzed the composition of the gases venting from this pocket, they found something disturbing. The ratio of certain isotopes indicated this wasn't old volcanic gas trapped since the last eruption. This was fresh gas, coming from magma that was currently molten, currently active, currently rising. The magma chamber wasn't static. It was moving. Slowly, yes. But definitely moving upward. This changes the timeline. Not dramatically. We're not talking about an imminent eruption next week or next year. But it does mean Yellowstone is more active than the official reports suggest. The USGS has always maintained that the chance of a major eruption in our lifetime is about 1 in 730,000. These new findings suggest that number might need revising. Maybe it's 1 in 100,000. Maybe less. Nobody knows for sure yet because we've never had data from this deep before. At 6.1 miles, they finally reached their target depth. The drill could go no further without risking catastrophic equipment failure. What they found at the bottom was exactly what they hoped for and exactly what they feared. A direct thermal connection to the magma chamber. Temperatures at the drill tip reached 896 degrees Fahrenheit. The rock samples brought up were partially melted, and the seismic sensors they embedded detected magma movement, less than half a mile below the drill tip. They had done it. They had reached the heat engine of a supervolcano while it was active. No one had ever done this before. Not at Yellowstone. Not at any major volcanic system. The data they're collecting is unprecedented. They can now monitor the magma chamber in real time. They can measure pressure changes, temperature fluctuations, gas emissions, seismic activity, all from inside the system itself. But here's where it gets really interesting. The original plan was to use this borehole to extract geothermal energy, to bleed off some of the heat and reduce the pressure that could lead to an eruption. But the discoveries they made changed that plan. The system is far more complex than anticipated. The supercritical water, the rapid mineral formation, the bacterial ecosystems. Everything is interconnected in ways we don't fully understand yet. Extracting heat could have unintended consequences. It might destabilize the bacterial ecosystems that could be playing a role in regulating gas pressures. It might change the circulation patterns of the supercritical water, potentially concentrating heat in dangerous ways. It might even trigger the increased magma movement by altering the thermal equilibrium. The margin for error is zero. One wrong move and instead of preventing an eruption, you cause one. So the current plan is monitoring. Learning. The borehole remains open with sensors at various depths constantly feeding data back to the Yellowstone Volcano Observatory. Scientists now have an unprecedented view into how a supervolcano behaves. And what they're learning is fascinating and disturbing in equal measure. For instance, the magma isn't rising uniformly. It's moving in pulses. Every few months, there's a surge of activity. Temperatures spike. Seismic activity increases. Gas emissions jump. These pulses seem to correlate with tectonic activity hundreds of miles away. When there's a major earthquake in California or Alaska, Yellowstone responds days later. It's like the entire Western North American tectonic system is connected in ways we're only beginning to map. The bacterial discoveries led to an entirely new field of study called deep geomicrobiology. Researchers are now drilling at other volcanic sites around the world to see if similar bacterial communities exist. They've found them at Mount St. Helens, at Kilauea in Hawaii, at volcanic systems in Iceland and Japan. Life exists in these extreme environments everywhere we look. And these bacteria might actually be helping to regulate volcanic activity by processing gases and minerals in ways that affect magma chemistry. Some scientists now theorize that the reason Yellowstone hasn't erupted in 640,000 years, despite being overdue according to its historical cycle, might be because of these bacterial communities. They might be creating chemical conditions that make eruptions less likely. It's a wild hypothesis, but the data is starting to support it. If true, it means we've been thinking about volcanoes all wrong. They're not just geological systems, they're biological geological hybrid systems. Life and rock interacting in a feedback loop that spans millions of years. The drilling project also revealed something about the nature of the magma itself. It's not a single uniform chamber of molten rock like we thought. It's more like a sponge, a matrix of solid rock permeated by pockets and channels of molten material. The magma is dispersed throughout a huge volume of rock, not collected in one giant underground lake. This is actually good news. A dispersed magma system is less likely to erupt catastrophically because there's no single pressure point that can fail. The bad news? It makes predicting eruptions even harder, because you can't just monitor one magma chamber. You have to monitor the entire sponge. Current estimates suggest that only about 5 to 15% of the rock beneath Yellowstone is actually molten. The rest is solid or partially molten mush. But that 5 to 15% is still an unimaginable amount of magma. We're talking about 500 to 1,500 cubic miles of liquid rock. Mount Vesuvius, the volcano that destroyed Pompeii, erupted about 1 cubic mile of material. Yellowstone has 500 times that amount sitting there, ready, waiting. The ongoing monitoring has detected other concerning patterns. The northern edge of the caldera is rising faster than other areas, about 3 inches per year, compared to less than 1 inch elsewhere. This suggests magma might be accumulating preferentially in one area. If that continues, if pressure builds up in one spot rather than dispersing evenly, it could create a weak point, a failure point, the place where the next eruption begins. Scientists are watching this area intensely. Meanwhile, thermal features across the park are changing. New hot springs appear every year. Old geysers change their eruption patterns. Ground temperatures in some areas have risen by 10 degrees Fahrenheit in the last decade. None of this indicates an imminent eruption, but all of it indicates something is happening. The system is evolving, changing, and we're monitoring it with tools and understanding that didn't exist even 10 years ago. The data from the deep drilling is being fed into supercomputer models that simulate magma movement, heat transfer, and pressure distribution. These models can now predict with reasonable accuracy what would happen if certain conditions changed. For instance, if there was a major earthquake directly under the caldera, or if the magma intrusion rate increased by a certain percentage, or if gas pressures reach specific thresholds. None of these scenarios are likely in the near term. But now we can model them, plan for them, potentially respond to them. There's also a fascinating economic dimension to this. If it could be safely tapped, the heat from just the shallow magma chamber could power the entire United States for thousands of years. We're talking about effectively unlimited clean energy sitting right there. But the risks are too great. For now, the technology and understanding aren't quite there yet. But they're getting there, fast. Some researchers propose a gradual, extremely careful geothermal energy extraction system. That's impossible. But to skim energy from the edges, to use the heat that's already venting naturally through hot springs and geysers. This could generate power while also potentially reducing some of the pressure in the system. It's a delicate balance. Too aggressive and you risk destabilizing the entire system. Too timid and you miss the opportunity to prevent a disaster while also solving the energy crisis. The Yellowstone drilling project represents a shift in how we think about natural disasters. For most of human history, we've been reactive. A volcano erupts. We deal with the consequences. An earthquake happens. We rebuild. But now, for the first time, we have the technology and knowledge to potentially intervene, to prevent disasters before they occur. It's terraforming in reverse. Instead of making hostile planets livable, we're trying to keep our livable planet from becoming hostile. But this raises ethical questions. Should we intervene in natural geological processes? What if our intervention makes things worse? What if by trying to prevent one disaster, we cause another? These aren't abstract philosophical questions. They're practical engineering and policy challenges that scientists and policymakers are wrestling with right now. Because the technology to intervene exists. The question is whether we should use it. The discoveries made by drilling into Yellowstone have implications beyond just this one volcano. There are about 20 known supervolcanoes on Earth. Bas in Indonesia, Tupou in New Zealand, Long Valley in California. All of them are active to some degree. And now we have a template for how to study them, how to monitor them, potentially how to manage them. International collaborations are forming to apply Yellowstone's lessons to other volcanic systems worldwide. What started as a drilling project has become a window into the deep earth, a laboratory for studying extreme life, a monitoring system for one of Earth's greatest natural hazards, and potentially a blueprint for disaster prevention on a planetary scale. The unexpected discoveries, the quartz crystals, the supercritical water, the living bacteria, the active magma movement, all of these have expanded our understanding of how our planet works. And they've given us tools to protect ourselves from forces that once seemed utterly beyond our control. Yellowstone isn't going to erupt tomorrow, probably not next year either. But someday, On a timescale we're still trying to understand, it will. And when it does, the knowledge gained from this drilling project might mean the difference between a manageable crisis and a civilization-ending catastrophe. That's why they drilled 6 miles into a supervolcano. That's why they risked everything to reach the magma chamber. And that's why what they found matters more than almost any other scientific discovery of the past decade. We're learning to read the planet's warning signs. And maybe, just maybe, we're learning how to respond to them before it's too late.